Bismillah ar-Rahman ar-Rahim. We have a finite alphabet, omega, of L letters. L is 2 or more. A sequence is generated. The letter in any position is independent of any other position, and in each position, every letter is equally likely to appear. The probability of having a particular letter is 1 over L. There is a specified string with length denoted with vertical bars around S. The question is, what is the expected number of trials to obtain that specific string for the first time? For example, if we are tossing a coin, then our letters are heads or tails, and we may ask this question. On average, we need to toss the coin how many times to get the sequence, say, heads, tails, heads. Given the string S, we define a polynomial C sub S of Z. This polynomial is summation R from 1 to the length of the string Z to the power R times eta R. Eta R is either 0 or 1. Eta R is equal to 1 if the prefix of S of length R is equal to the suffix of S of length R. A prefix of S is a non-empty substring of S that occurs at the beginning of S. A suffix of S is a non-empty substring at the end of S. Suppose that our alphabet contains the letters ABC and the string of interest is CABC ABC. If R is equal to 1, we compare the very first letter in the string and the last letter. They are equal, they are the same. So eta 1 is equal to 1. If we take these two letters, that's CA, these two letters BC. These are different substrings. Eta 2 is equal to 0. If we take the first three letters, CAB, the last three letters, ABC, they are different. Eta 3 is equal to 0. The first four letters are CABC, the last four letters are CABC. We have equality. Eta 4 is equal to 1. The first five letters, CABCA, the last five letters, BCABC, the prefix and suffix are not the same. Eta 5 is equal to 0. Also, eta 6 is equal to 0. The prefix of length 7 is the same as the suffix of length 7. That's the full string S. So eta 7 is equal to 1. The polynomial CS of Z that is associated with this particular string is Z, because eta 1 is equal to 1. So we have Z to the power 1 plus Z to the power 4 plus Z to the power 7. As we will see, it turns out that the answer to our question about the expected number of trials to obtain a specific string for the first time actually depends on this polynomial here. Define G of n to be the number of strings of length n that contain no occurrences of string S. N is a non-negative integer. If n is equal to 0, we set G of 0 equal to 1. We define the generating function big G of Z as summation small n from 0 to infinity G of n Z to the minus n. Define f of n to be the number of strings also of length n, but those strings end with S at the right end, and they contain no other occurrence of S. F of n gives us the number of strings of length n that has one occurrence of S only, and this occurrence is at the right end. There is a generating function associated with f of n, summation n from 0 to infinity f of n Z to the minus n. Note that by definition, f of n is equal to 0 if n is less than the length of the string, because f of n counts the strings in which S occurs exactly one time. So you need S to appear. N must be the length of S or more. If a small n is strictly less than the length of S, then f of n is equal to 0. We need to obtain this generating function. The way to go is to obtain these two guys together. Consider any of the Gn strings that do not contain S. Among the strings of length n, there are G of n strings that do not contain S. To those strings, append any one of the letters from omega to its right end. For instance, if the letters are ABC, each string from those Gn strings generates L strings of length n plus 1, where L is equal to 3. Because you will take the string and append A, take the string, append B, take the string and append C. So in total, if we do this operation, we end up with L times G of n distinct strings. Each one of those guys is of length n plus 1. Those L G of n strings either do not contain S at all, or if they contain S, S appears at the right end of the string. Note that our starting strings are completely free from S. When you add one letter, you end up with a string of length n plus 1 with no occurrence of S, or if S appears, it appears in the rightmost position. Based on this idea, we can write down that L times G of n is equal to G of n plus 1. This is the number of strings of length n plus 1 that do not contain s, plus f of n plus 1, the number of strings of length n plus 1 that has exactly one occurrence of s in the rightmost position. Multiply both sides by z to the power minus n. Then sum over non-negative integer n. On the left-hand side, we get L summation n from 0 to infinity, g of n z to the minus n. This is the generating function, big G of z. We get L g of z on the left-hand side. On the right-hand side, after multiplying by z to the minus n and then summing, we get these two sums here. Multiply each sum by z, but it was not there to compensate. We need to have here z to the minus 1 and z to the minus 1. So we have summation n from 0 to infinity, g of n plus 1, z to the minus n plus 1. This is exactly the generating function without g of 0. When n is equal to 0, this is g of 1, z to the minus 1, plus when n is equal to 2, we have g of 2, z to the minus 2, then g of 3, z to the minus 3, and so forth. What is missing from here is g of 0. So this is equal to z. We have the generating function, but without g of 0, and we set g of 0 equal to 1. The same idea is here, but note that f of n is 0 for every n that is less than the length of the string, and the string has one letter or more, so small f of 0 is equal to 0. On the right-hand side, we get z g of z minus z plus z f of z. Rearranging the terms, we have big f of z is 1 plus g of z multiplied by L minus z over z. We have now one equation relating f of z and g of z. We need another one so that we can solve for g of z. Consider string A of length n. A does not contain s. So A is one of those g of n strings of length n that do not contain s. Append the string s to A to obtain the new string B. B is of length n plus the length of s. It contains s at its rightmost end. We are sure that string B contains s by construction. But where is the first appearance of s within the string B? Because of the structure of the string s, it may happen that s appears for the first time in B with its rightmost letter in position n plus r, where r is 1 or 2 all the way to the length of string s. For instance, consider omega to be the three letters A, B, and C. Suppose that string A ends in CAB. Suppose that S is our friend from the previous page, the string CABCABC. If you attach this to the string A, you will get those guys here. This whole thing is string B. The first occurrence of string S within string B is here. Whenever we take a string that does not contain S and then append S, we get a new string. Now S is guaranteed to occur within the string. It appears for the first time with its rightmost letter in positions n plus 1 or n plus 2 all the way to n plus the length of s. If this statement is true, it must be the case that eta r is equal to 1. The prefix of string s of length r is identical to the suffix of string s of length r. This is a string A, which does not contain s. This is a string B, which is A and s adjoined to its right end. If the first occurrence of s within B ends here in position n plus r, this means that string s appears somewhere here. By construction, s is the last part of B. If this part of B is s and the very last part is s, then the last r letters of s are exactly the first r letters. Eta r is equal to 1. The conclusion is that g of n, the number of strings of length n without s, is equal to a summation over r. And in this sum, we put f of n plus r. F of n plus r is the number of strings of length n plus r, where s appears exactly once at the right end. The strings that we start with are split into groups. The rth group has the first occurrence of s in B, ending in the position n plus r. For this to happen, eta r must be equal to 1. We can write down this sum with index small r from 1 to the length of s, and then we multiply f of n plus r by eta r. Note that given any string counted by f of n plus r, there is a unique way to extend that string to a string of length n plus the length of s with s at its right end. Multiply both sides by z to the minus n and then sum over the non-negative integer n. We get g of z on the left-hand side. On the right-hand side, we get this expression. Multiply by z to the r and z to the minus r. We have this summation here. If n is equal to 0, we have f of r z to the minus r. If n is 1, we get f of r plus 1 z to the minus r plus 1, and so forth. This summation is exactly the generating function big F of z, but it's missing those terms, f of n times z to the minus n, where n is from 0 to r minus 1. Note that the maximum possible value of n is r minus 1. And so any n here is strictly less than the length of S. Thus, f of n is exactly equal to 0. All the terms here are equal to 0. For every r, this summation is big F of z. We can take it as a common factor. The remaining polynomial is Cs of z. F of z is equal to g of z divided by Cs of z. From the previous page, f of z is 1 plus g of z times L minus z over z. Now we have an equation we can solve for g of z. G of z is z Cs of z over z plus Cs of z times z minus L. Our goal is the expected number of trials till we get the string of interest for the first time. If t is the time of the first occurrence of the string S, the expected value is the probability that t is equal to n times n, and then we sum n from 1 to infinity. This n here can be written as summation k from 1 to n of 1. In this double sum, we sum n from 1 to infinity, k from 1 to n. We are summing a real valued non-negative quantity. So by Tonelli, we can do the summation in any order of our choice. If we interchange the order, we have k from 1 to infinity. N sweeps through the integer values that are k or more. What is this summation? We have the probability that t is equal to n and n is k or more. This is exactly the probability that the time of the first occurrence is greater than or equal to k. The expected number of tries that we are interested in is summation k from 1 to infinity, the probability that t is greater than or equal to k. What is this event? The first occurrence takes place in strings of length k or more. This event is equivalent to saying that every string or every sequence of length k minus 1 letters does not contain S. What is the probability of this event? What is the probability of any specific string of length k minus 1? For a particular sequence of letters of length k minus 1, the probability of having the required letter in its position is 1 over L if we have a total of L letters. The letters in each position occur independently of any other position, and they are equally likely. The probability of each letter is 1 over L. And since we are talking about strings of length k minus 1, then the probability of any particular sequence of length k minus 1 is 1 over L to the power k minus 1. The event of interest is that we have a string of length k minus 1 that does not contain S. So we need to take this 1 over L to the k minus 1 and multiply by the number of strings of length k minus 1 that do not contain S at all. And by definition, this is small g. Small g of k minus 1 is a count of the number of strings, the number of sequences of length k minus 1 free from S. This probability here is g of k minus 1 times 1 over L to the power k minus 1. The expected number of trials is summation k from 1 to infinity, g of k minus 1, 1 over L to the k minus 1. If we put n equal to k minus 1, when k is 1, n is 0. When k tends to infinity, n tends to infinity. This summation here is sum n from 0 to infinity, g of n, L to the minus n. And this is exactly the generating function g of z, but z is replaced by L, the number of letters in the alphabet. The answer to our question is this generating function with z replaced by big L, the number of letters in the alphabet omega. We have here z minus L, so if z is set equal to L, this disappears, and then L in the numerator is cancelled with the L in the denominator, and we are left with Cs of L. If we are doing coin tossing, so we have two letters, H and T, heads and tails. What is the expected number of tosses till we get HTT for the first time? To answer this question, now we know the final result. We need to obtain what is the polynomial associated with this particular sequence. We have HTT. The first letter is different from the last letter, so eta 1 is 0. HT is not TT, eta 2 is 0. Then eta 3 is 1. The polynomial here of HTT, if we write it in terms of z, is 0 times z plus 0 times z squared plus 1 times z cubed. If we put z equal to L, which is 2 in our case, we get 2 cubed, which is 8. On average, we need 8 tosses till we get HTT for the first time. Let's consider another sequence, HHTH. The first letter is the same as the last letter. The prefix of length 1 is the same as the suffix of length 1. Eta 1 is 1. But then we have HHTH. These are different. So eta 2 is 0. HHT is not the same as HTH. Eta 3 is 0. Eta 4 is equal to 1. The polynomial is z plus z to the power 4. If we replace z by 2, then we have 2 to the 1 plus 2 to the 4. That's 18. For the sequence HTHTH, eta 1 is equal to 1. Eta 2 is equal to 0. Eta 3 is equal to 1. The prefix of length 3 is HTH and the suffix is also HTH. Eta 4 is equal to 0 and eta 5 is equal to 1. The expected number of tosses to obtain HTHTH for the first time is 2 plus 8 plus 32. That's 42. Suppose that the alphabet contains the decimal digits 0, 1, 2 all the way to 9. L is equal to 10. What is the expected number of tries to get the string 4, 5, 6, 7, 8? Note that for this string, eta r is 0 for r equal to 1 or 2 or 3 or 4. Only eta 5 is equal to 1. The expected number of tries is 10 to the power 5, 100,000 tries, till we get 4, 5, 6, 7, 8 for the first time. If S is 5 sevens, note that here all the etas from eta 1 to eta 5 are equal to 1. And so the expected number of tries is 10 plus 100 plus 1,000 plus 10,000 plus 100,000. 111,110 tries on average.